All right, and welcome back for our last lesson in our reaction rates. So applying equilibrium constants. The idea is we know that if a reaction goes to equilibrium or reaches equilibrium, which they all will eventually, and if we know at least one of the starting concentrations as well as the K equilibrium, or for that matter, if we know the equilibrium concentration, it sets us up with a algebraic formula that we can solve for. We have A is equal to M over B, or in the case of chemistry, we have K is equal to P over R. So we can use that to solve for the new concentration that you'll reach at equilibrium, or if you have the concentration equilibrium, you can solve for the initial concentration. It allows us to do quite a bit of material. So let's take a look. A mixture of 0.5 molar H2 and 0.5 molar I2 was placed in a 1 liter flask at 430 degrees Celsius. The equilibrium constant for this reaction, hydrogen plus iodine equals hydrogen iodic gas, is 54.3 at this temperature. So there's our K. Calculate the concentrations of all three species at equilibrium. So we can now use this K equilibrium to predict how much product will actually form, given 0.5 moles of iodine and 0.5 moles of hydrogen. What we use to do this is what's called an ICE table. Your initial concentration, the change, and equilibrium. A lot of times you only see one column for change, hence the word ICE. I've got two changes here in terms of X and then total overall change. So let's go ahead and plug in what we have. Initially, we have an initial concentration of H2, which is 0.5, and of I2, which is 0.5. Our initial concentration of HI is 0. We don't have anything yet. What's going to happen during the reaction is that X amount of H2 and X amount of H2 are going to react to form 2X HI. 2 because of the coefficient 2 here. Notice with I2 and H2, the same amount will react, which makes sense. It's a 1-to-1 ratio for I2 and H2. So again, setting up our K equilibrium, our concentration of HI at equilibrium will be HI, concentration squared, divided by the hydrogen ion concentration and the iodine concentration. We can plug in the variables that we have, and we know, go back a second here and explain this, we know that our initial concentration for H2 will be 0.5, and at equilibrium we will have reached 0.5 minus X. So that's where this comes in right here. The iodine is the same story. We have 0.5. We're going to lose or use up X of it, so 0.5 minus X. And then our HI will be 2 times whatever X is, so 2X, and we're going to square it. So in order to solve for this, I'm going to take the square of both sides. Again, you notice down here on the bottom, it's 0.5 minus X. 0.5 minus X, that's the same thing. That's the same as saying 0.5 squared. So if I take the square root of both sides, I'll not only get rid of the squared 2 up here, but I'm also going to get rid of one of the 0.5 minus X values down here. And we end up with just 2X over 0.5 minus X equals the square root of 54.3, which was 7.36885. Now I want to get 0.5 minus X off the bottom, so I'll multiply both sides by 0.5 minus X. Remember to distribute, so we've got the parentheses around it, that kind of helps. 0.5 times 7.36885 gives me 3.684425, and X times 7.3688 gives me X. So now I've got X on two sides, but my numbers are off the bottom. Next step, I'm trying to get my x's on the same side, so I'm going to add that 7.3688. Remember, it's a subtraction step here, so I'm going to add it to the other side. I should have underlined digits here. That's why you see the underlined digits there. They aren't underlined. That's a mistake. And finally, we're solving for x. So we divide both sides by 9.3688 to get that off the side with x, and we'll end up with x by itself. So my final concentration, my final x will be 3.93. That's not necessarily my final concentration. Let's take a look. So for my H2, remember x tells me how much H decreased by, so it's not really the final concentration. In terms of x, it started at 0.5 and went down by 0.393. I2 also started at 0.5 and went down by x, so it went down by 0.393. Whereas HI, its new concentration is going to be 2 times 0.393. I can do the math now. 0.500 minus 3.93 means my concentration of H2 at equilibrium will be 1.107. Same for my concentration of I2, and my concentration of HI at equilibrium, 0.786.